Hi, this is a quick lesson about error. Because anytime we work with numbers, of course, there can be error in our measurements and our procedures. Two of the things you're going to learn to do in this lesson are how to differentiate accuracy and precision, and then learn how to calculate percentage error from lab results. So here's the two definitions. Accuracy is how close a measured value is to the accepted or true value, and precision is that reproducibility of measurements. To give you an example, here's a bullseye, and this right here, obviously down here in the bottom corner, is both accurate and precise. Okay. The other one in the bottom corner, this is precision, where it's like reproducible, but it's not accurate. I will sometimes get students in lab that get a wrong answer, but they say, well, we measured it a couple of times and it agreed every time. But maybe, like, do you ever have a ruler where, like, here's the ends of the ruler, but then, like, here's zero? Maybe they didn't line up what they were measuring with the zero. They accidentally lined it up with the end every time. So they were wrong by the same amount every time. So when something like this happens, I would say here, maybe the sight is off on the bow if this is, shooting arrows at a target. In lab, I would say, maybe the instrument is not zeroed. Maybe, there's something that is systematically going wrong every single time. And while they're getting reproducibility, it's still not the right result. Now, this is no accuracy, no precision. This is really concerning in lab because, that they're, I'm sorry, wait, this one is no accuracy, no precision. Very concerning in lab because they have, of course, numbers that are all over the place, and they're not, when you average these numbers together, you're going to get an answer right in here, and it's not going to be right. Here, they're not precise, but their answers are going to probably average out to give them, a decent result. That happens sometimes, especially when we're timing something and it's, starting and stopping a clock. Sometimes you stop it a little too soon, sometimes a little too late. If you repeat it, 5 or 10 times, though, usually your results, even though it's hard to like stop that clock, you will kind of dance around the actual, and your average will give you, an accurate answer. So of course, this down here, though, is what we're shooting for, to be able to have reproducible answers that are also quite accurate. Now, one of the things you will often have to do is calculate the percentage error. The reason we want the percentage error, not the absolute error, like, let's say the absolute error in a measurement is 1 centimeter. In some cases, that's fantastic. Like, if you're measuring, for example, the length of a house, to only miss by a centimeter, that's not much. That's not bad. Relative to what you were measuring, that's not bad. Whereas if you're measuring the length of your pinky finger and you miss by a centimeter, well, that's kind of careless and bad, because your pinky finger is not that many centimeters long. To miss by a centimeter is a pretty good portion of what you were measuring. So rather than talking about absolute error and say, well, my answer was only off by a centimeter, well, relative to what you were measuring. So that's why we have something called absolute, or excuse me, percent error, where we compare the, and I'm somehow not, oh gosh. Yep, we're back. Okay. Where you somehow compare the absolute error, like that 1 centimeter. How much did you miss by, to the accepted value? What's the accepted value for the length of the house in centimeters? What's the accepted value for the length of your pinky in centimeters? So our equation, and you can always look this up on the internet too if you forget to put this in your notes. This is a really good idea to put this in your notes, okay? The absolute error is the difference between, what you measured, like the observed value and the actual or the accepted value. Okay. That's the absolute error. And you want to take the absolute value of that because sometimes the accepted value might be a little higher than the observed value. Like, maybe you measured the length of something and you got 9.8 meters, but the accepted value is a full 10 meters. So yours was a little low. The difference being the 0.2 meters, but when you take the absolute value of it, you would make it a positive 0.2. We will compare that or ratio it to the accepted value and then multiply by 100 to put it into a percentage. Let's do an example together. So student measures the volume of a block to be 3.34 centimeters cubed. This would be, must be too close to the top. That'd be the observed value. Okay. The actual volume, so this right here, this is the accepted value, right? Because that's the actual accepted volume of this block. So to get the percentage error in this measurement, remember we take the observed value, 3.34 centimeters cubed, and honestly, they just have to be in the same units, and the units are going to divide out then anyway. So sometimes, as long as they're in the same units, sometimes people don't even put the unit in the problem. Take that difference, and then we're going to divide by the accepted value. This is where that centimeter cube is going to divide out, and we'll multiply by 100. So let's do our math. If we take 3.34 minus 3.50, we get negative 0.16 centimeters cubed. Now, taking the absolute value of that is going to change the sign. Okay, see that? The centimeters cubed will divide out. To get your answer, you take the 0.16 divided by the 3.50 times 100. This is a constant, so it's not going to limit our sig figs. This has 2 sig figs. This has 3 sig figs. So when we divide and multiply by 100, our answer is going to be rounded to 2 sig figs. And we got 4.6% for the. Here's another one for you to try. What I'd like you to do is pause and do this problem. And identify the observed value and the accepted value. Plug them into the equation. When you are done with this problem, you're only going to be able to have 1 sig fig because the subtraction on the top is 0.6, and rounded to 1 sig fig, it comes out to be a 0.7% error. If you have trouble getting that answer, make sure you check in with your teacher to ask them why. But that's pretty much it. The difference between accuracy and precision. Accuracy is how close you are, like getting to the bullseye. Precision is, can you reproduce your results? And then once you do reproduce, your results and you calculate your observed value, what's the percentage error of that compared to the true or accepted value? So I hope that helps. And good luck with, with the end here of the practice that you did. And there'll be some problems for you to practice applying this error calculation. Good luck.